Hey everyone, this is Hitler, and I want to answer some questions about the kind programming language in a way that shows more of the workflow and the thought process and the heuristics that go into proving theorems with kind. And I think video it's better. You can see how things really work in practice, whereas in in text it's not always very clear. So these questions are from Ferran. He's a math student from Barcelona, and he asked three questions. The first is, does kind have tactics? Are the syntaxes that are documented in syntax MD, are they tactics? And how would you prove this equation in kind? Well, answering the first question, tactics are like a separate language that's not meant for programming. It's meant for just proving theorems, and kind doesn't have it. In kind, the language that you use to program is the same language you use to prove theorems, because sometimes you need to mix the two, and sometimes the boundary between programming and proving theorems is blurred, and it wouldn't make much sense to separate the two. But the way we found to make proofs shorter and less work intensive are the syntaxes, which are just shorthands. They are things that you could write in kind using just function applications and for alls and lambdas, but that would get really big, and we use syntax to make our programs, both our programs and our proofs, shorter and more legible. So they are like tactics because they help you reduce the amount of work you need to do, but they're not a separate language. They're part of both programming and proving theorems. And to prove this equality, well, I first started explaining right away how to prove it, but I think it's best if we go step by step, dealing with each technique separately, so that we can really get comfortable with the full proofs. So the first examples are about universal quantification. When you need to state that for all numbers, natural numbers a and b, a plus b is equal to b plus a, you write it like this. And here there's a proof. So this is we are saying that for all a and b this is valid, but this is also a function. So what does this mean? What happens if we call, for example, net com a 2 3. Well, when we do that function application, that substitutes the instances of a for the concrete values. So this is a proof by specialization that 2 plus 3 is equal to 3 plus 2. And we could use this down here to prove that 2 plus 3 is equal to 3 plus 2. Oops. Okay, we got our first error. And this is important because errors will happen, and if you see them and how I fix them, you understand you will deal with them better if you get them. So the problem is that kind is reading this as 2 plus this equality, but an equality isn't a natural number. This here doesn't make sense, so we'll add parentheses to avoid this error. By default, all kind will always read everything like that. There's no operator precedence or anything like that, so I recommend you use parentheses whenever you can. If you're dealing with something that's associative like addition, then don't bother with parentheses. But if there are many different operations involved, I recommend using parentheses whenever you can. So, okay, we have just seen proof by specialization. And we'll use it again here. Right now, we want to prove that for all A, we have this equality. This time, we substitute A with A, kind of funny, and B with 3. That's not working because I erased that lemma. But it's already proven in the standard library. It's right here, and it's called not add com. So we just add and add right here. Now that's more like it. Add the parentheses. All right. So if we go back to the proof we want to make, how would we write that proof using ordinary prose, using a normal math proof? We would go like this. I see two ways to do it, and both ways we can translate to kind. The first is, well, by commutativity, b plus c is equal to c plus b. And since we can do the same operation to both sides of an equality and get another equality that's also valid, we add a to both sides, and we are done. We have proven the equality. We could also start with a plus b plus c is equal to a plus b plus c. And that's valid because those expressions are identical. And we call this the reflexivity of equality. And we go to this expression right here and use commutativity to replace it with c plus b. That's what we call a rewrite. And again, we're done. So each of these techniques, how do we write them in kind? We'll start with reflexivity because it's the fundamental one and it's the easiest. To prove something by reflexivity, we just write halfly. And what kind we'll do is, here look, we want to prove that A is equal to A. Can I do it by reflexivity? Here look at this variable right here and compare the other to this one. If he can see it's equal, then he'll accept the proof. If not, he'll give an error. For example, if I put a 0 here, then reflexivity shouldn't work. Let's see if it does. It doesn't, because by reflexivity we would have 0 equal to 0, not A equal to 0. So that's good, kind isn't accepting nonsense. And another important thing is that when kind is comparing things, he'll do some computation. I mean, if we put concrete values, it will reduce it and see if they result in the same number. Like here, both sides of the equation aren't written the same, but kind can compute these values and see they are equal. Kind could even reduce terms when some symbolic values are involved. For example, here, even thought he kind doesn't know what A is, it can reduce this term right here. So I hope that works. I haven't tried this yet. It doesn't, but that's because of some missing parentheses here. Now it does. Cool, very cool. Another thing about reflexivity that isn't very well documented yet, it's that sometimes reflexivity, we want to prove the goal. We already have the goal, but sometimes we want to define a local lemma. For example, let's say I want to define a lemma. Let us call it lemma. And I want to prove by reflexivity that 73 plus 1 is equal to 73 plus 1. Now, this is a very specific equation, and I haven't written anything that lets kind know what equation we are trying to prove, and kind can't read our minds. So let me put a hole here so we can see what happens. And kind doesn't know what to put here. To tell kind, we have to make a type annotation like this. If we do that, we can define our local lemma. And if this is a part of a bigger proof, we can use that lemma to do our computations. So that's all we have to say about reflexivity. Now let's talk about apply. Apply is the part of proof 0 when we added 0 to the left of both sides of the equation. The first thing we need to know in order to use apply is how to define lambda functions. Like this. Suppose we want to define a local variable that's a function that takes a natural number and adds 3 to it to the left. How could we do that? We could define it as a global function, like that. And say it's 3 plus a. Then that would work. That would reduce to first to global func and then to 3 plus n, and then kind would substitute this by 2, and then it would get the answer 5, just like we want. But sometimes we don't want to make a global function. Sometimes we just want to make a function that will be used in the body of this definition and nowhere else. What we do then is to write it like that. And the type, just like if it were a global definition, and 3 plus n, or m. You could use any letter here, it doesn't really matter. So if we do that, it also works. So we have defined with f the operation of adding 3 to the left of a natural number. So let's go to the next example. Now we are supposing that a is equal to b, and we want to prove from that 2 plus a is equal to 2 plus b. The way we do that is we call apply. Here we put the function, the operation we want to apply to both sides, and here we put the equality we want to apply. So what function are we trying to apply to both sides of the equation? The operation of adding 2 to the left. So we can write it like that. N is a natural number, and we'll add 2 to the left of n. And the equality is this one, our hypothesis. Oh, we have another hole here. Let's just put a string. Cool. So our apply has turned this equation in into this equation. And we can finish our proof right here because the theorem is already proven. Very cool. Wait a little. When oh, okay, it's out of order. I thought not all theorems were being defined. Okay, so let's talk about Hirites. Hirites are when we have a large equality and we want to rewrite just a small part of it, like this. We can define, we want to prove this equality right here, which we have already proven with apply, but we want to do it with rewrite this time. The first step is to take as a lemma that 2 plus a is equal to 2 plus a. Let's put a hole so we can see what variables are defined and what are their types. So we have proven that 2 plus a is equal to 2 plus a, but we want to rewrite that a right here with b, because we know that a is equal to b. And the way we do that, let's call this lemma 0 and lemma 1. It could be like this, that's no problem, but just so we can refer to both of them, let's do it like this. So we take lemma 0 and rewrite it. And we write it like this. Rewrite x in 2 plus a is equal to 2 plus x with our hypothesis that tells us that a is equal to b. Let's see if that works. It worked. Now we have 2 plus a is equal to 2 plus b. And so what this does is it looks at x, the x spot, and sees if it's equal with the left side of the equation you put here, and if it is, it will replace it with the right side of the equation, in this case b. And something that's very useful when doing rewrites is to put holes in the expression, because you don't want to retype all the expression when you're doing proofs, because sometimes these expressions can get really big. So since kind already knows this equation, when he sees this hole, he can tell that 2 plus a should go in there. You don't need to write it, it already knows. So let's try that and see if it works. You can only know for sure if something works if you run the type checker and see the answer it gives you. This time it worked. Let's see if we can put another hole right here. It works. Oh no, it doesn't. That was an error. Okay, so kind needs to this two right here. Maybe if we do it like this. Yeah, now it works. Sometimes this plus doesn't work as well as it should. Yeah, it can't. We have to put a 2 right here. Alright, but then we can return that lemma and the theorem will be proven. Alright. Now we can go for the proofs. Oops, ignore this. This was just something I was playing with earlier. Let's put the proofs right here so we can look at them while we are writing our kind proofs. And the first step in proof 0, it should define commutativity. This equation from commutativity. And from the for all example at the start, this example right here, we already know how to do it. We just call the theorem of commutativity of natural numbers. So we do it like this, BC. And that's a lemma. We haven't proven our theorem yet. Nice. We have another hole. Where is it? Oh, it's down here. Let's comment this. Okay, so we have b plus c is equal to c plus b. Nice. Now we need to apply a to both sides of this equation. And we do this like this. Let key d equal to apply any notch and a plus n, and we put lemma right here. Now we have our final equation, and we can say kid, the proof is done. Cool. Now let's try the rewrite method. So to rewrite, first we define the lemma with reflexivity that a plus b plus c is equal to a plus b plus c. That didn't work, and that's because again we forgot our parentheses. It happens. Okay, so we have a plus b plus c is equal to a plus b plus c. Now we need to rewrite this little part right here. And we'll do this with let key d equal to lemma rewritten like this. Rewrite x in a plus b plus c. But I bet kind can infer that is equal to a plus x with we don't have defined, we haven't proven that b plus c is equal to c plus b. So let's do it. Let's put a hole right here. Let's call it equality, and let's call com is equal to net.add.com bc. Now it's defined. Now we can put com right here. The rewrite was successful, and this is our final equation, which we can return key ed. So that's it. These are some more techniques that you can use and that are more like what you use when you're using theorems that are already proven, like the commutativity of addition. So I hope you find this useful. If you have any more questions, you can ask them in Kind's repository. You can send me messages, and I'll try to answer them as best as I can.